It's official, folks. Looks like we can get started. For today's class, we're going to move through section 7.7. We've got a couple more, I think about 3 more examples we want to take a look at in approximating integrals. After that, we're going to start breaking into the section of improper integrals. This is a bit of a longer one, so it'll definitely take more than just one class meeting to get this one through. This one's probably about 2, potentially 2.5 class meetings. We'll see how long it takes to look at the main problems and move through this one. But that's where we're at so far in the course. When we come back on next class, we'll just be 1 class period away from our upcoming exam 1. Again, we have the exam materials that's posted here. Keep in mind that you can have a single page of notes allowed on this exam, kind of just reiterating just because it's good. It's our first exam, good to reiterate this a lot. And also don't forget, you can bring a calculator to this exam as well. It's a good thing to have, but it's not going to be something that's majorly used on each problem. But in case there's an approximation or you just need to check if numbers are reasonable, it's nice to have that creature comfort, the calculator. So that's where we're at so far. Any questions or comments whatsoever, folks, so far or at the moment? Okay, well, let's get started on our section 7.7 then. Section 7.7, I'm just asking these exercises here. So make sure you only do part A of problem 7, part B of problem 9, and so on, or else it's a pretty tedious homework set. And essentially all we're doing is approximating integrals. We have the left endpoint rule, the right endpoint rule, and the midpoint rule. But we also just derived the trapezoid rule before we end the class on Monday. The way it works is the trapezoid rule is the average of ln and Rn. ln is just saying the left endpoint rule with n subintervals. That's the right endpoint rule. So if you average those approximations, you get this brand new rule. So the trapezoid rule is indicated this way by just saying Tn, T for trapezoid, N for the number of approximating rectangles. It takes a similar feature, but watch out for the delta x divided by 2. For the midpoint rule, left endpoint rule, right endpoint rule, it was always just delta x. But now some of these formulas are changing bit by bit. Also, there's a number pattern that goes in here. You always start with x naught. And after that, it goes 2 times x1, 2 times x2, or excuse me, 2 times f of x1, 2 times f of x2 is better said, all the way to 2 times the penultimate term, f of xn minus 1. Then the pattern stops. We just have ordinary xn at the far right. So another thing that's kind of interesting here is if you're doing a right endpoint, or excuse me, a trapezoid rule with n being the number of approximating rectangles, inside here is n plus 1 terms, which makes your work feel kind of weird. We're used to using, say, midpoint rule. If it's in midpoint rule with 5 terms, or excuse me, with n equals 5 approximate rectangles, you'd write down 5 terms. Let's take a look. Did we do that? Here it is, the midpoint rule with 4 terms, 4 approximate rectangles. And sure enough, we wrote 4 terms. But starting with the trapezoid rule, that breaks down as well. It's all because of the problem of taking the far left endpoint and the far right endpoint gives you an additional term altogether. So this is like 1, 2, 3, really, and so on. Aside from that, the rest of it's kind of business as normal. First thing you want to calculate is the delta x. After you get delta x, you find what xi is for all values of I, and just crank out the formula right here. So we'll give it a try with this integral. That's where the revision is on these notes. That was a minus, and it looked like it was going to be just fine until you put it in a computer and you realize with a minus, that gives you complex numbers on that domain. So change it to plus and now everything's happy. Any questions at all, folks, before we give this one a try? Okay, well, let's start off by saying what we're about to do. That whole integral is extremely complicated to get an exact answer on. I'm not sure if it's possible, but for back of the envelope approximation, it's approximately equal to T for trapezoid rule 5 with 5 approximating rectangles. First thing we ought to do is just write out the formula. That helps a tremendous amount. It's going to be delta x halves multiplying, and here's how the pattern starts. F of x naught plus 2f of x1 plus 2f of x2 plus 2f of x3. I'm always looking to this number. So next it's plus 2 f of x4. I'm one off from 5. That means I start dropping the 2's and just say f of x5. I thought I was writing on a straight line, but that kind of got a little crooked. That's all right. So there's all of our terms in a row. Next, let's calculate delta x in this problem. Delta x is always formula b minus a divided by n, no matter what rule you're using. B is the upper limit of integration, -2, minus -3 for the lower limit, halves. So this gives us altogether 1/2, or a 0. Oh, hang on, I made a mistake on there. It looked good to start. Anyone see what the mistake is to that stage? Something's amiss with that. Thank you, absolutely. This must be the 5 that we saw here. Thanks for spotting that. So watch out for that. That has to go down there, and using this formula, that's the n value. So now trying this out again, this is positive 1/5. And 1/5 is just fine if you like fractions. The next problem I'm going to keep fractions in because it's a third. It's not easy to give a good readout on that. But it's easier for me to write out 0.2 rather than a fifth. So I'm just going to deal with the decimals on this one. I tend to do that a lot more in an exam setting just because, I mean, in a timed exam, you want the numbers to be kind of nice and cooperative so you can just move through the problem, not get hung up on fractions. In the homework, it's all up to you. So now that we've done that, the very next thing I'd probably do at this stage is find the values of x0 through xn. X0 is always the lower limit of integration. So that would be the -3 we see here. Then we're ready to give a value for x1. Anyone spot what it should be based on our work so far? Yep, absolutely. Good call. All we're doing is we're taking the prior value, -3, add delta x to it, and so -2.8, as you said. Let's add here on the notes. All we did was go plus delta x. And then we just keep repeating that pattern. The next portion of the paper I'd be looking at is right here. We have to land on -2. If we don't, something is amiss. I would have discovered if I put a 2 there and left it there, something was going off. So keep on adding. This one is going to be -2.6, then -2.4, -2.2, finally, -2. It matches the upper limit of integration here, so it tells us we are now on the right track. Well, just about there. Let's write this all in. This is now equal to, moving through the problem, delta x was a 0.2. So we're taking 0.2 halves. Or 0.1 you can write down in if you prefer. It's going to multiply these things. So we have to know, what did we mean by f of x? We were referring to that integrand right there. So it starts off, here's the tedious part, square root e to the power of, I'm going down the line with these values that we indicated. So it's -3 plus 1. Then just keep on moving through. Next one is going to be plus 2 times the square root. E to the power of the next value, -2.8, plus 1. And just keep on going. Your hand could get tired doing this after a while. So 2 root e -2.6 plus 1 plus 2 root e -2.4 plus 1. And just double checking. Okay, we still need a 2 root e to the power of -2.2 plus 1. And here's where we have to make a notational trick. There's sometimes just going to be a lack of paper going horizontally. I'll always, in this case, just carry down to the next line, plus this one. Notice we don't put the 2's here any longer. Now it's just going to be root e to the power of -2 plus 1, and then close the bracket. So there is our entire computation. And we made a comment about this if it was an exam question. So let's reiterate it here. This is for full credit on exam 2. So if this was an exam 2 problem, I would say that this is a completely reasonable stopping point, only because exams are timed, and this is where the calculus ends. Going beyond that is still important. We'll do it on the homework. We'll do the approximation, but save time on the exam. I'm mostly looking on this format right here, that you can nail the form using the trapezoid rule. And I did want to highlight in blue just to convey we got that stuff from the integral. Well, we're going to do the next exciting step of putting all of that into the calculator. But any questions or comments at the moment, folks? Okay, so that's the trapezoid rule. My claim is it approximates that integral there. And there's different things you could do to check this out. For example, you could go to Wolfram Alpha. We explained it up there in the notes to see what a better approximation would be and how it would compare with the one down here. They should be pretty close into the same ballpark. Also, we showed how to use Desmos if we wanted to calculate this extremely rapidly. I want to do that again because, again, it's pretty rapid. We save some class time. But not everyone wants to use Desmos, and that's completely fine. I'll show how to do it on a different calculator as well. So let's go ahead and do that. The calculator I'll use is going to be this one. So kind of your standard calculator. Fortunately, this one's not allowed in an exam setting, but I'm bringing it to class because it's the only one I can emulate and actually show on a Zoom setup like this. So using this calculator, let's see, I'm going to hide the participants window for just a minute. Sorry about that, folks. It'll come right back. We need to do the tedious job of jamming that into the calculator. So this is the kind of hold my beer moment. Let me know if my numbers go sideways or anything like that. Just to start off, let's put in a 0.1. Then a parenthesis, then a root. E to a power, it's e power -3. You can get your e from right here where the natural log button was. And I got the root from over here where the power 2 button was. So second, e to power -3, and plus 1. So there's our first term already. Now we're moving on to the next ones. 2 times, and that's not going to work. Let me try again. Plus, there we go, 2 times. Now you can imagine this is the reason why I say this is a good stopping point on exam. Because if you had to go further, you're losing a lot of time, and you're losing points just because of accuracy in this calculator. This is actually pretty hard to do, so let's keep on going. Second, power 2. Second, natural log for the E button, -2.8. Right arrow and plus 1. Then right arrow again to get out of the root. I think that's what I was messing up over there. Plus, let's do it again, 2 times. Second root, second power E. Now it's -2.6. Plus 1. Oh, and that's the wrong plus 1. That's going to mess it all up. Calculator is very tedious. This is almost a cell for Desmos, I'd say. Plus 1. And now plus 2. Take the root. Take the exponential. I mean, at this point, I almost feel guilty because it's extremely tedious. I can see it on people's faces, but figured if this is on the homework, we ought to do it at least once in class, especially for folks who would rather not use Desmos. So almost there, 3 more to go. E to the power of -2.4. Right arrow to get out of the E function, plus 1. Right arrow to leave the square root function. And I think I'm on this one. Plus 2 times second power 2 button, second logarithm button, -2.2. Right arrow plus 1. Right arrow to leave the root. And now we're breaking the pattern, no 2 times. So just second. Oh, that's going to mess it up. Hang on. We do need a plus. That'd be terrible to make a mistake right at that spot. And then second, square root. Second natural log. Now it's just -2 plus 1. Leave the root, close the parenthesis, and my claim is that should be about right, as long as no weird symbol got typed in incorrectly. That looks like a familiar number, so I'm getting, I'd say 4 decimal places is a reasonable amount to round to for this kind of problem, especially if there's no indication in the instructions. Just use your best judgment, you'll be totally fine. I'll take this to positive. Let me move this over just a touch. This is an approximation again at this stage, so 1.0419. I'm going to go a little bit further so I don't have to round with carry. So 196. Well, any questions, folks, on that demonstration of the calculator or use of the trapezoid rule? Okay, so if this was a real homework problem and you missed the number right here, I think I would take out at most a half a point, something like that, because once again, this is the calculus. And if you're really doing this for the sake of getting a good approximation, you're probably not using 5, you're probably using n equals 50, which means you're probably using computer software. You might be doing a for loop. You're not even using Desmos in this case. But this is, again, an introduction to numerical analysis. So this is what it would look like when we were just breaking into those topics. Michael says, but if you make a mistake, you can just scroll up, select the entire equation, just make changes to a particular mistake instead of retyping everything. Yeah, absolutely. Thanks for mentioning that. I mean, this does have a couple creature comforts. You can hit second answer. No, that's not what you meant. You could go scroll up again, hit enter. And now this is an editable field. So if we made a mistake here, like Michael's saying, you can find the mistake, that's a lot of scrolling, and then make the change. Honestly, I think the T83 is easier because it doesn't scroll to the right, it just goes down. It's easier to go up and over, find the mistake. This one is kind of tough scrolling through all that stuff. Well, other questions or comments, folks, so far? Okay, I should probably delete that just so it's not a confusing comment to leave over. So that's how the trapezoid rule goes. And for certain problems, it's not a bad rule. I mean, it's going to always beat, well, almost always beat the left endpoint rule, the right endpoint rule, because it's averaging 2 different types of rules altogether. But if we want to get a really fast approximation, we might be using something entirely different, Simpson's rule. Now, this one's weird. We did the derivation for trapezoid rule, but only this one to the reading for the curious. What's going on with Simpson rule is we're not using rectangles to approximate like the midpoint rule. We're not using trapezoids like in the trapezoid rule. Instead, we're fitting a degree 2 polynomial into 3 different adjacent points. So that is very wild. And the book shows what the derivation would look like for that. But here's the side effects. If you're using polynomials to approximate your function, not rectangles or trapezoids, the algebra, once you work through all of it, is going to give us a delta x over 3. And the pattern, which was 2, 2, 2, 2, starts off like this. Just like trapezoid rule, there's a constant of 1, a coefficient of 1 on f of x naught. When it starts with a 4 and begins to alternate, 4, 2, 4, the alternate continues all the way down to the penultimate term, f of x n minus 1. So the pattern starts at 4, alternates 4, 2, 4, 2, so on, and it will always, no matter what, end at 4. Then we just have a coefficient of 1 on the constant term. That's a bold claim. There's no way it always starts at 4 and always ends at 4. That depends on n. So if n is even, then that's absolutely true. So the Simpsons rule is kind of nice to talk about after trapezoid rule because it's way more powerful and it's a tiny modification to trapezoid rule. Division by 3 and a 4, 2, 4, 2, 4 pattern instead of 2, 2, 2. So that's a rule there. It's a really tough one to derive. So once again, if you're curious, take a look into the book on how that goes. What we'll do in class is just practice of implementing it. We'll try it on this integral right here. And then we'll try it again on an applied problem just to see what all this stuff is really good for. Any questions whatsoever, folks, on Simpson's rule before we...
Simpson's rule only works when n is even.
Absolutely,
That's a stipulation. Okay.
Yeah. Right. And it's really a side effect of the derivation. The outcome of that derivation is the 4-2-4-2 pattern. And that pattern could only ever work if n was even to begin with. So I would have to give you a problem that's going to be something like n equals 4, 6h, something like that. Any other questions so far? Okay, and I like how you mentioned that, where that's a stipulation. Let's kind of highlight that even more. N must be even. Must is a really strong word in mathematics. It means the rule is just not going to work if you had an odd n. So that's a really weird constraint on this rule, but it's worth it. It's extremely powerful at approximating. So let's give it a try with that thing. Natural log 1 plus x squared. I'm not too sure if I could integrate that, but we can absolutely approximate it. The steps always begin the same way. You want your delta x. It's going to be 6 minus 4 divided by 6. We're using 6 approximating rectangles. So this is 2/6, giving us 1/3. And this is the context where I probably would keep it a fraction or 1/3, since putting this in as a decimal number, sure, we could go 0.3 bar, but I feel like to me that's kind of gets a little bit messy to work with. So keeping it as a fraction, if you decide to go that route, next step to take is, let's just write down the rule for this particular case. We'll say that total integral is approximately S, now standing for Simpson's rule, 6 for the 6 approximate rectangles. So that's that part right there where the approximation begins. Formula goes delta x thirds. Then starts off with f of x naught, coefficient of 1, and it always begins with the 4 to begin the alternating 4-2-4-2 pattern. So plus 4, f of x1, 2, f of x2, 4, f of x3, 2, f of x4. And at this point, it's a good idea to start looking at that part. We're going to end on 6. So when we go to plus 4, f of x5, that's our ending term right there. So now we just add, oh geez, I ran out of space. Down below, we'll add plus f of x6. So that's the Simpson's rule pattern indicated down here finally. Next thing to do is just fill in the values for x naught through x6. X naught's not so bad. It's always lower limit 4. But it's awkward now because, well, I have this right here. Sure, you could use mixed numbers, but those are awkward to put in a calculator. What I'm going to do is use 4 as a 12/3. So now with the 12/3 all set up, we're adding delta x 1/3 to each new value. So this one is now 13/3, 14/3, 15/3, 16/3. And remember, we have to end on 6. So this is a pretty good check on our process so far. 17/3, meaning this one is 18/3, which is in fact 6. So we've got the pattern down and the right values for all of the x values. So we're just about there. Now it becomes the most tedious step of all. We need to write this stuff in. If this is a real exam question, I would probably say n is 4 because I'm not worried about the tedious of writing down all of these terms. We're doing a little bit more since the homework is asking for a little bit more. But keep in mind on a real exam, I've tried to keep these a little bit constrained. It's all about the concept, not about writing down a whole bunch of stuff. So next, delta x. Let's substitute in here. It's a third thirds, so you might call it a ninth if you prefer. I'll write it this way just for a paper trail in the notes. And here, our f of x function, that's referring to the integrand, which is the natural log 1 plus x squared. So we need to write that in a bunch of times. It goes natural log 1 plus, I'll start with the 4 squared since that's easier to write than the 12 thirds, plus 4 times natural log 1 plus 13 thirds squared. That's kind of awkward to write in. I might save some horizontal space going this way. 1 plus 13 thirds squared, not by much. Then it's going to be plus 2 natural log 1 plus, I'll go sideways, 14 thirds squared plus 4 natural log 1 plus 15 thirds squared. So we're up to this turn, just 3 more to go. Definitely riveting stuff. Next one is plus 2 natural log 1 plus 16 thirds squared plus 4 natural log 1 plus, I lost my place, 17 thirds squared. Your hand and your brain kind of gets numb after doing this for too long, but we're almost there. Plus natural log 1 plus 6 squared. So that's the entire function, or excuse me, the entire approximation through Simpson's rule of the original integral. All that's left to do is crank it out. Any questions at all, folks, with the form we have so far? Okay, and there's no trouble putting in the calculator other than it takes time, and if you make a mistake, it's pretty hard to see sometimes. So let's go to Desmos route once again, just for the folks who might like to kind of streamline this process. So if you're putting this into the Desmos calculator, the very first thing you want to input is the integrand f of x, highlighted here in blue. So fx equals natural log 1 plus x squared. Next thing you do is, I'm just going to copy in this statement with the right values of 12 thirds, 13 thirds, starting with here, that's a 1/9. Let that go a little bit further so we can focus on the computation. So it's 1/9 times f of 4 plus 4 f of 13 thirds plus 2 f of 14 thirds plus 4f 15 thirds. I guess that's 5, but that's no real need to simplify that. We're just going to calculate it. Plus 2 f of 16 thirds. See how much space we can actually get on this. Now we're up to this one, plus 4. Oh, there we go. Plus 4 f of 17 thirds plus this last term, f of 18 thirds. Oh, I guess that's 6, but that works just as well. Close your parentheses. And this is my claim for the approximation, 6.4923. Provided I didn't make any mistakes, copy that in, 6.4923. Well, how's that look to folks so far? Does that make sense on using the Desmos as an alternative calculator? Awesome. It's all up to you what your preference is on the homework. On the homework, we do have to calculate them, but just to remind ourselves again, on exam, you would stop at this line right here. There's no reason to waste the additional exam time computing stuff. Save all of that for the actual homework. So pausing out this problem a little bit longer, if you were doing this as a homework problem, sure, it's one thing to get this into the calculator and get a number out, but it's a whole other thing to know if the pattern was right in Simpson's rule. So if you want to further check, let's do that once again. You can now go to something like Wolfram Alpha. I'm sure there's other sites, but this is just my go-to for this kind of thing. Yeah, you abused it quite a lot as a student, trying to figure out if my numbers are on the right track. For that problem, you could say integrate natural log 1 plus x squared from x equals, I think we want to go lower to higher to not confuse Wolfram, x equals 4 to x equals 6. And definitely don't pay them any money. I would just go down to what they give us. They say the approximation is 6.4923. Notice how remarkable that is. We have an even more accurate answer, 6.4923122 and so on. But for what they gave us, let's see if they give us more digits. You know what? We're pretty spot on. I'm kind of curious now. So 6.492312224, 6.492314. It differs on that decimal place right there. So just 6 terms gave us a pretty overwhelming amount of accuracy on this problem. But that's because we're using a pretty powerful numerical analysis tool, Simpson's rule. Not using rectangles, it's using polynomials to approximate area under this thing. So that's pretty wild stuff, even though it's a fantastically more powerful tool. Notice in the numerical analysis, the formula barely changed at all. So if you're interested in that stuff, ISU offers 2 semesters worth of numerical analysis getting into these kind of matters. Any questions at all, folks, on the conclusion here? Okay, so now we can approximate rectangles. And here's what the real value might be. Sometimes you just can't get an antiderivative, but other times, like our author mentions, sometimes you don't even have the function. For example, this graph right here was produced by just taking data points and connecting the dots. We don't have the function to this thing at all. Should kind of want to reformat how this is shown. Let me put it up like that. So the story behind this data is it's telling us, shown to the right now below, is the graph of traffic on an internet service provider T1 data line from midnight to 8 a.m. So 0 for midnight, 8 a.m. here, going T for hours. They tell us the variable D is the data throughput measured in megabits per second. So that's the variable D going this way. And notice that's a rate. We have a net change theorem from Calculus 1 that says, if you integrate this rate of change, what you're going to get is the megabits. So they're asking us, use Simpson's rule to estimate the total amount of data transmitted during that time period. So we're going to find the total megabits from midnight to 8 a.m. Somehow, some way, we'll make that happen. But this problem looked really fun at first. This is a screenshot I just stole from our course text. But then when I went to try to solve it at home, I got really annoyed by it. I wouldn't see anything really annoying about the presentation of this information, the wording and the graph together. I didn't see it either, in all honesty. I saw this problem, I thought, it's going to be fine. It is fine, but it's a little bit more tedious than I expected because we really have a unit mismatch. Time is in hours, and the data rate D is in megabits per second. We need to do a unit change or else we're kind of stuck in the water on this problem. Definitely annoying, but let's make it work. So let's do it over here. I'll start with maybe this value, 0.4. Well, obviously it could be any value, but let's take that one. 0.4, and this is, I don't know the unit for megabits per second. Let's just assume it's MB. If anyone's better at data science than me, let me know what the right unit is, and we'll definitely put it out. So say again? Lowercase b, thank you. Well, that would be megabytes then with uppercase. So megabits. Now, that's a major unit thing already right there, right? So getting that right is tricky. So 0.4 megabits per 1 second. We need to take this into minutes. So 60 minutes per 1 second. I don't do a lot of this kind of work. I skipped all chemistry classes, physics classes as an ISU student, so this is foggy work for me sometimes. Next, it's 60 minutes. for the 1 hour. Then we have cancellation of units going, uh-oh, what'd I do here?
You have to go 1 second, 60 seconds.
Yeah, I got this all backwards. Let me try again. Because I want to cancel the second unit. I should have went 1 second per 60 minutes. We got a chat to come through. Mbps. Oh, that's awesome. Mbps. Thanks for spotting that, Michael. Our unit is improving all the time. So times 1 second. Oh, that's what I'm messing up. Thanks for spotting that. So 60 seconds to the 1 minute conflates with 60 minutes to the 1 hour. Thanks for spotting that. I think that's better unit so far. That look all right to everyone at the moment?
The way you have it set up is megabits per second per second.
Oh, you're right. So it really was MB like that because we have the per second already indicated here. Thanks for spotting. I don't think I would have ever saw that. So that is a really fine detail about the unit there. So again, the problem is kind of annoying, but you know, it's a real world problem. It's all messy. That's how stuff happens. But we're on the right track. Here's our cancellation. And now we're just going to take the 0.4 times 60 times 60. Yeah, I didn't see that either, Michael. Thanks for mentioning that. Mbps would be the right thing without the fraction being put in. Learning all sorts of stuff about this problem. So now finally, let's get rid of all this right here. We've got 0.4 times 60 times 6, or squared is probably the fastest way to type that out. So that turns into 1440. Let's go equals 1440. And now let's use the unit that Michael indicated. Megabits per second, like that. Oh, you're right, megabits per hour. So after getting through all the units, I think we're on the right track. So that 0.4 is now, I'll just call it a 1440. Now we're using the right numbers here. And gonna need this calculator again. Let's divide this by 4. 360 is the actual length right here for the first tick mark. So that's 360. So that means that would be 720. 1080. Oh, didn't quite think that through. 1080 going that way. And a little bit more to calculate. 1440 plus 360 gives us 1800 megabits per hour now. It would have been so nice if they just gave us the right units to start off, but again, that's kind of a value to realize that we've got extra problems right here. Times 2, now we're at 2160. Times 3, and we've got 2520. And finally, times 4 is going to give us our 2880. So that's the most annoying part about the problem. The rest of it's pretty awesome. We're going to take this data rate in megabits per second, now convert it to megabits per hour, and find the actual amount of megabits transmitted in this entire time frame. Any questions at all, folks, on the setup on this one? Yeah.
Wouldn't you also need 3240 for D at the top left, since it goes up almost the top?
Oh, you're right. Just, yeah, it gets way up there. Let's add one more. Thanks for spotting that.
3240.
Yep, absolutely. 3240 for that last tick mark. So now that we've done all of that, we go back here and it says, use Simpson's rule to estimate the total amount of data transmitted. Total amount of data transmitted, I'll delete this in just a moment, but just to visualize, that's just referring to this area. So now suddenly approximating that area becomes really vital. We don't have a curve to help us, but that's okay. We can just read the numbers off the graph. It's a little bit of fudge work here. If this was a real exam question, I'm not going to make you do the unit changes. I think it's way surprising out of nowhere on the exam setting. But if this was a real exam problem with the right numbers put in, you're just reading off the graph using numbers in the right ballpark. So there's going to be variations in answers, and that's okay. So let's say here, the amount or the total data is going to be approximated through, it says Simpson's rule with n equals 8. So let's call that S8, just to organize our thoughts. Once you have S8 down, we want to write down the pattern for this thing. So this is going to be equal to delta x thirds. It's multiplying f of x naught for f of x1 to f of x2 plus 4 f of x3 plus 2 f of x4 plus 4 f of x5, 2 f of x6, 4 f of x7. That's the penultimate term, so we break the pattern and just say plus f of x8. So there's our numbers. I'm going to take a screenshot since I think we need to scroll just a little bit more. Okay, so that ought to work for us, I hope. So now, I guess the next thing we need to calculate that I neglected to do earlier is delta x. Delta x, well, we're not looking at integral, but the lower and upper limits of the integral would have came from the horizontal axis. So we're finding the area from 8, the upper limit, minus all the way down to 0, the lower limit. We're using 8 approximating rectangles indicated here at S8. So at least this part, delta x is nice. It's just a 1. That's helpful since our units are in 1 hours per. So next we'll go, this is equal to 1/3. And when we say f of x naught, well, that was just the formula for the pattern, but we really should be referring to that function here, the data throughput. So grabbing those values, starting off on this one, x naught is going to be 0 right over here. And, well, we're just giving our best estimate possible. That looks like it could be maybe, I'll call it 1200 megabits altogether. Then the next one's going to be plus 4 times. We're at this value. This looks like it's pretty close to 1080. So I'm just going to cite that value. If we were doing this as a real problem for, say, Idaho Falls Fiber or something, they'd give us the actual numbers that created the graph. But here, this is the limited tool we have. We're just reading it off. So plus 2, f of x2. And you know what? Might have helped to just put in 0, 1, 2, 3, 4, 5, 6, 7, 8, just to help out to direct us where we're going on our x values. So next, we're at 2 hours. This one looks to be about 1440. Then plus 4, I'm off to 3 next, and at 3, this one's close to 1800, it looks like. So now up to 4. At 4 hours, the data throughput is pretty stable for that time period. Something, I guess people are pretty tired around that time. So 1800 again. Plus, coming down here, 4. Now we're at 5. So at 5, the data throughput, this one's kind of hard to see. How about, what would you all say? 2000, I like that. Let's go with that. Now we're up to 6 hours in. you know, 5 hours, 6 hours looks about the same. So if we said 2,000, I'm probably gonna just stick with it. Again, your numbers could be quite a bit different. It's okay if it's in the right ballpark. So 2,000 again, but let me double check. Where am I at? I'm at 6 hours. So I need to put in a coefficient of 2 ahead of that. Then 2,000. Now we're at the 7-hour mark. Here's the last time we'll use a coefficient. So +4. At the 7-hour mark, data throughput is about 2880, it looks like. Then final one. Michael says, will there be a question like this on the future exam where it could be a lot of variation, possible approximation? I absolutely agree with the variation on this one. If I did make this question a real exam 2 question, I would probably try to arrange it so the actual line hits the grid mark a little bit more exactly. So that even if you're fudging it, it'd be by a little bit. This one would be a pretty nasty one to actually grade because, yeah, looks like there could be a lot of variation in answers. So it could be a real exam question, but probably a better graph and definitely no unit change stuff. That's better left for homework when we have the time to carefully consider it. So last one we're putting in is at the 8-hour mark. And that one is about, what would you all say for at 8 hours? What's the best number for that?
3,100.
I think that sounds about right. Plus 3,100. So there's the whole thing finally. Now we're ready to give the approximation. At this stage, any calculator is going to do the job. There's nothing special about this format, just a whole bunch of numbers. I'll use this one just because it's available and quick. Still, there's just a chance of mistyping something, so go carefully. Let me know if I'm getting something different. 1/3, 1,200 plus 4, 1080 plus 2, 1,440 plus 4, 1,800 plus 2, 1,800 plus, now we're down here, 4 times 2,000. There's a like terms. You could have just said 6 times 2,000. And then finally, 4 times 2,880 plus 3,100. So finally, we've got a number that data third point is 1,500,273.3 repeating, it looks like. Or excuse me, 15,273. 3 repeating. And I mean, repeating is kind of silly because this is a pretty blunt approximation, but that's how the calculator landed. I'll just stick with that. But what's the unit on this thing again? Let's take a look. These things had units of megabits per hour. We're multiplying by hours because this delta X actually has a unit. This is in, once I get that color to switch, hours as well. We took the actual horizontal axis to form delta X. If that's in units of hours, and this is in and this is in megabits per hour, we just get megabits itself. So coming down here, the unit on this thing is megabits. I'm not too worried about your unit in the final answer, but it's just the nicest way to format the answer. If you missed that, it's not a big deal, but this one did require a unit change. The real homework question for this one, you have a graph about like this, but no weird unit changes that you have to maneuver through. So that's kind of interesting. I don't know what was transmitted over the internet, but it was used by that amount. Again, rough approximation though. Any questions at all, folks, so far? Okay, how can we tell if it's in at least a decent ballpark? You could do one more test on this. Let's look at that graph. This is a really, really blunt way to look at this. Don't imagine it's just a triangle or rectangle like this. You could find the area going this way, area going that way, or if you want an even blunter approximation, look at this area. Just one triangle. It should be in the neighborhood of the 15,273 that we found. We know it's way off. It should be an undercount. So let's see if it really is. That's the wrong calculator. Let me grab this one. So my last back of the envelope check, more of a sanity check on this, is find the area of that triangle. It'll be 1/2 times the base. The base is h for the 8 hours, times the height. The height would be 3240. And this comes out at about 13,000. Looking at what we have here highlighted, that is a massive underestimate, right? We want the area under the red curve. So it feels comforting that our estimate is 15,000. It's a good amount more. It puts it in the right ballpark of what we expect. But this is about the best answer we can give using Simpson's rule. So we did it, folks. That's numerical approximation. Really, it's just a subset of numerical analysis. A whole bunch of different things happens in that kind of class. But any last questions or comments on finalizing these last problems? Okay, let me save this up. I think next time I run this problem, I'm going to put in the right units here. And thanks for everyone with the help on getting the right unit down. I'm going to definitely remember that next time I try to do this problem again. So we're done with approximate integration, and that takes us to section 7.8. This is the last one of chapter 7, so congratulations everyone, we're making it through. Chapter 8 is going to be shorter for us. We're focusing exclusively on applications. Chapter 9 will look at some introductions to differential equations, and we'll be about through midterm at that point, I'd say. But now for section 7.8, it's just a whole nother adventure. And we're trying to do this now. Let me get my windows in their right setup. Microsoft is always a little bit weird about this stuff. Oh, I think I see what's up. Okay. So improper integrals. There's a couple types that we're going to be taking a look at. But what makes it an integral improper is whenever you have a problem with potentially the limits of integration, or you have a problem with the function itself. Here, the problem is the limits of integration are infinite. So that means you can't use the fundamental theorem of calculus whatsoever. Fundamental theorem of calculus says, if you're integrating this kind of function, you first go here, you find your antiderivative, then the assigned area under this curve from A to B only depends on the boundary points of that antiderivative. Honestly, every time you think about that, that's a pretty wild statement, but it does have its limitations. It's assuming you have a closed interval A to B, those are finite numbers, think 5 to 12, for example. You cannot actually put infinity inside there and actually use the fundamental theorem of algebra. Nonetheless, this is still important. This is used in probability. We'll find other ways this comes into play. Probability is used everywhere. We still have to find a way to actually approximate that integral, some way, somehow. So what is it even saying? It's saying you're taking a curve 1 over 1 plus x squared. So there's the curve. We don't care about the full domain on this thing. We want to go from 0 to infinity. So let's go 0 less than equals x less than equals, well, what do we even put, right? It's can be something large, but that's not fitting the problem either. But this is the graph of the curve at least. Starts off with some definite area right away, but then the curve approaches the x-axis rapidly. Now, anything can happen with this, but keep in mind, blow that up a bit, this curve never hits the x-axis. It's never negative, it's never 0. So it approaches the x-axis, but no matter how far you go to the right, there's always a separation between the curve and the axis. So if that's the case, if you're asking the question, what is the integral here from 0 to infinity? It almost feels as if the answer is always infinity every time, right? There's always area to the right. Yet that's not true. Sometimes, even though there's always area to the far right, I mean, we can look at it. Despite that fact that their area exists and it keeps on going to the right forever, this might converge to an actual finite number. Just depends on the function. So we need to find that number, and here's how it starts. You cannot use the fundamental theorem of algebra here, of calculus right here, because of the infinity, but you can do something else. Just try to approximate it. That's a poor approximation. We're going from 0 to 1 when we should be going to infinity. But you can use the fundamental theorem right there. Antiderivative is tangent inverse, and all I did is do the calculation. Tangent inverse of 1 minus tangent inverse of 0. Tangent inverse of 0 is just a 0. So the area is so far 0.785. But what we need to do to get a better approximation is we need to increase this, because we're intending to go off to infinity. So the next level of approximation, this is what it looks like. We're going off to 10. That's a better start, but looks like we've just about doubled the area, right? 1.471. Now, the graph changed a lot because the horizontal scale got so wide. If you go up to 100, then notice it went from 1.471 to not much of a change. The area seems like it's starting to stabilize. This is at 100. If you go up to, say, 1,000,000, 10 to the power 6, it only changed in the 100th spot. So it looks like this actually stabilizes. It appears that the integral from 0 to infinity of 1 over 1 plus x squared dx converges. What we mean by converges is that there is a finite number that expresses what we're trying to do here. Find an infinite area. Or I said that weird. We're trying to find the area of a region on an infinitely long length. The interval of integration is what's infinite, not the area. So we just keep on increasing the size of the upper limit of integration, but there's a better way to express that. You're trying to make the upper limit larger and larger and larger. Why not just put a variable t there and say, take the limit as t goes off to infinity. That's the trick behind this kind of improper integral. It just delves down, becomes a question of, does this limit, as we form the antiderivative and keep on calculating these things through the fundamental theorem, will it stabilize? Does the limit exist? If it exists and it's a finite number, we say it converges, and the integral equals that number. We'll say the area, the total area going off to infinity, is also defined to be that number. So that's the idea behind all this. We convert this integral to a limit as t goes to infinity. So the infinity here gets wiped out and replaced with the variable. Kind of weird stuff, but that's what we're getting into very next. Any questions at all, folks, with the run through of the idea behind improper integrals, type 1? Okay, the notes are long only because it takes a minute to kind of say what we're even doing. But here's the first actual legitimate definition that our author gives us about all this material. An improper integral type 1, sorry, let me just find a good zoom amount. Type 1 just implies, oh, that's not a pen. There is an infinite interval of integration, meaning the interval that we're considering has infinite length. This is going from a to infinity. A is going to be just an ordinary finite number. Think 0, pi, something like that. We could also deal with something that goes like, say, this one. If you have a negative infinity as opposed to a positive infinity, you just take the limit as t goes to the negative infinity, and you throw in t for the lower limit of integration. If it's up here, then t goes into that numerator or upper limit of integration here to replace the infinity. So that's the name of the game. Wherever your limit or infinity is, we throw a limit statement, replace the infinity with the new variable t. So those are two types already. But the weirder types even still go like this. You can integrate something from negative infinity to positive infinity. In probability theory, that's done essentially all the time. For example, the normal curve, let's get a really quick look at that. Standard normal curve density function, misspelled that, but Google's smart, so is a function defined, let me see if I could get a better topic. Where's Wikipedia when you need it? There it is. The normal probability distribution, something people hear about all the time, normal curves and such, they're defined by that integrand right there. Pretty crazy function, but the worst part about it is it's an exponential function. It's very tough to integrate, but you can integrate this thing. Let's see if they give us any information here. That's it. Wikipedia pages have a way of getting out of control. But the punchline to this is, if you take this function right here, what you do in probability theory is you integrate it from negative infinity to positive infinity. And because it's a real probability density function, that integral comes out as exactly 1. And it's kind of remarkable. Every probability density function has to do that. And so this is just a way to say, although this is really esoteric, it has immediate practical applications just right out of the gate for this kind of work. So back to this problem though, if you have to integrate something at an infinitely long interval of integration, a negative infinity and a positive infinity, what you do is you find some real number a. Often we pick 0 just because it's convenient in the work when you're finalizing the answer, and you split it into 2 integrals. Go from negative infinity to a, think 0 maybe, then go from a to positive infinity, and you now have to show both of those converge. If one does not converge, the whole thing is divergent. So that's the whole spiel of dealing with improper integrals type 1. We often say these words. We say an interval is convergent if the limit exists. And we say the interval is divergent if the limit does not exist. And this is kind of a preview of terminology. We're going to use this terminology a lot when we're in chapter 11. We'll say a series is divergent or is convergent and so on. And in fact, these kinds of things also come back in chapter 11 as well. Usually it's this one up here. So that's the whole spiel of how it's all defined. The author does give us one nice formula. I didn't do an example on this because this is already an example in the reading, but this integral right here is pretty important. Integrate 1 over x to the power of p. This is convergent as long as your power is positive, greater than 1, and it diverges for all other cases. So that's something we'll also come back to in chapter 11 quite often. So it's just mentioned here as a kind of a preview of when it will need it. So we've got about 4 minutes. We don't have enough time to even really get too far in this question, but we have enough time to start it. When we come back on Thursday, we'll take a look at how these go. But this is always the required step 1. We have to say what we mean and really mean what we say. And this is extremely vague when you're saying you're integrating from e to infinity. The way we make this concrete is we say we're really doing this. We're taking the limit as t goes to infinity of the definite integral now from e to t of 1 over x natural log x squared dx. So that's our required first step. We have to indicate the limit, and we have to take the infinity, send t into that direction, replace infinity with that t there. Then we're on the right track. From then on out, it's just a matter of solving this, finding antiderivative, and then taking the limit. But I don't think I want to rush through the very first question on these notes, so we'll come back to this on Thursday's class. Any last questions or comments, folks, on what this setup looks like? Okay, so really awfully weird topic, but it becomes a little bit more routine and more easy to navigate through once we just get used to the extra symbols being thrown around and their meanings. But have a great night, folks. I'll see you all in Thursday's class. You bet. Have a good one.